Now let's talk about even and odd functions. This is really going to be a talk about symmetry. A function is even if the graph is symmetrical with respect to the y-axis. And you will see this definition that the function's value at any negative number would be the same as the value at the positive number. That definition is a textbook definition, and basically the even functions graphically are separated by the y-axis. There is that symmetry in which you fold a piece of paper along the y-axis, you would be able to match up both sides of that graph. On the other hand, if the function has an odd symmetry, then it's symmetrical with respect to the origin in the center. And this type of symmetry is more of a diagonal side instead of side-by-side symmetry. There are some functions that have no symmetry at all, as you will see. Now, let's do a couple of examples. This first example asks us, is the function even, odd, or neither? Notice the exponents are both even exponents. If you have even exponents, then the function is even. That means it has a symmetry with the y-axis. Just to prove that fact, you could compare h of positive 1 and h of negative 1 to see what happens. H of positive 1 would be 2 times 1 squared plus 1 to the 6th, which is 2 times 1 plus 1, which is 2 plus 1, which is 3. When you use the value negative 1, 2 times negative 1 squared plus negative 1 to the 6th, then you end up with 2 times 1 plus 1 because all those negatives multiplied together give you a positive, and 2 plus 1 equals 3. This will always happen with an even function. Even though we could tell it was even by the exponents, to prove it, you would want to substitute in a positive value and a negative value and make sure that they are equal. Now the second example, if you notice, you have odd exponents. The exponent on the second term is an understood 1. If it's odd exponents, then the function is odd. An odd function is a diagonal symmetry about the origin, as we had earlier defined. Now, if you use this same concept with the positive 1 and the negative 1, you will notice you get opposite answers. For instance, if I plug in positive 1, 1 to the 5th minus 3 times 1, that's going to be 1 minus 3 times 1, 1 minus 3, and that's a negative 2. If I substitute in negative 1 to the 5th minus 3 times negative 1, then I get negative 1 plus 3, which is positive 2. Notice those are opposite signs. When they're opposite signs, then you do not have symmetry. Now, this last example is neither even nor odd. It has no symmetry. I can tell by looking at the exponents. The first exponent is even. The second exponent is an understood 1, and that's odd. Since those exponents are not the same type, then this has no symmetry. Now, let's think about symmetry in terms of real life and art. Symmetry that is even is a side-by-side symmetry. Here's an example of someone who hung pictures in their own home, and notice the symmetry like the side-by-side. Now, they use different colors, but the frames are actually hung on what we call an even symmetry. Here's another example of even symmetry where pictures are evenly spaced and they're evenly hung side by side. And last but not least, here are some albums that are hung above a sofa side by side. Now, odd symmetry is different. It's a diagonal symmetry. Notice here's another photo setting, and it's more of a diagonal setting. They're hung on a diagonal, these pictures are. Along this stairwell, you'll notice someone has created a tree branch, and in process of that, gone with more of a diagonal symmetry. And last but not least, we'll see some lanterns that were hung along a staircase, and that is again at a diagonal, so that is an odd symmetry. Now some problems do not have symmetry at all. Here's an example of no symmetry at all, as you see this strange arrangement of the bicycles on the side of the wall. Now let's take a look at these examples of graphs. The first graph we would say is even, because it has that symmetry about the y-axis side by side. The second graph we would say is odd. It goes through the origin, and notice that it has a diagonal pattern about it. Part of the graph is in quadrant 1, and part is in the diagonal opposite quadrant 3. The next graph over is even. Again, it's side by side through the y-axis. And the last graph over on the right is odd. Again, it has a reflection across the origin, and it is in quadrants 1 and 3, more of a diagonal. On the lower level, we see another example of an even symmetry. Everything is symmetrical about the y-axis. And then we see the odd symmetry. And again, it just so happens to run through quadrants 1 and 3 on a diagonal. Now remember, any of these graphs can be taken and the symmetry removed. For example, if I take that first parabola that's written upside down and has even symmetry, if I shift it away from the y-axis, then that's an example of a graph that has no symmetry at all.